Yes. Hello. Am I audible now?
Hello? Yes, sir.
Okay. Yes, actually, after sending you the link, I found that it was not seen. So I called on your number and it said it is pushed off. So I thought I don't know, some problem is there.
Actually, sir, I'm working in post office now. So some in my post office section, people are getting my phone numbers and they are calling me without any reason. So I just switched off. I just on my aeroplane mode.
Okay. Okay. No issue. So, okay. So let us start the session. So in the yesterday's class, we discussed about the Gauss law and electric field.
Gosh.
Yes.
Yes, sir. Yes, sir.
Yes, but there actually, I didn't discuss the electric field due to the line charge and surface charge distribution. So first
Mm.
today I will discuss the topic and then
Okay.
also we will derive the same expression using the Gauss law, means application of Gauss law.
Okay.
Okay?
Okay.
So first,
Okay.
okay, so very quickly let us have a look here. See. How first, let me start with this question. Then it will be better. If you see,
Mm.
find the total charge inside the volume indicated by rho v given as 4xyz square, where limit of rho is 0 to 2, phi is 0 to pi by 2, and z is 0 to 3.
Mm.
Okay. Now,
Okay.
yes, all the values are in SI units. So we have to find the charge, total charge.
Okay.
This is the question, and we have to find the total charge. So see, if you see this
Gosh.
question, why I have selected this, because this will give you some idea. See, rho v is given, fine, 4xyz square. From seeing here, you may say that this is the Cartesian coordinate system, right?
Yes. Yes, sir.
But if I look here, the
But
limits,
it here. Uh,
this is in which coordinate system? With rho, phi, and z.
Cylindrical.
Cylindrical. So now you have to find the Q, that is the total charge. The question is find the
Mm.
total charge. So charge is, we know that, integral of rho v dv. Yes,
Okay. Yes, sir.
rho v is given, but thing is that now how shall I take the dv? Shall I take the dv like this? dx, dy, dz?
Uh, no.
No, because I don't know the limit of x, y, and z.
Okay.
I don't know the limit of x, y, and z. So I
Z.
cannot take this. So then what can I take? I know the limits of this rho, phi, and z. So I can take the dv in the cylindrical coordinate system, and which is in the cylindrical coordinate system, what is the formula for dv?
Uh,
Hmm?
R sin theta.
R sine
R
theta.
sin theta.
In cylindrical coordinate system.
Cylindrical coordinates. Okay. R dr d phi dz.
Yes. R dr or
Dr d
yeah,
phi.
yeah. Rho 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 d rho d phi
Ah.
dz. It is same.
Rho dr.
Telling correctly, same time.
Mm.
It is the same thing, that is the rho. So it is rho d rho. Very good. You are remembering this rho d rho d phi dj. Right?
Yes. Mm.
Okay.
Yes, sir.
Fine. I will take this.
Okay.
No, no problem. That is dv is will be like this. Then again the challenge remains here that this is Cartesian, this is cylindrical. So I will have to
Mm.
express, I cannot integrate because this is in terms of x, this is in terms of the rho, d rho, d phi and dz. So I will have
Mm.
to express this x, y and z in cylindrical coordinate system. So how to
Mm.
do this?
X equal to
to rho
r cos theta.
phi.
R cos theta.
Not
Cos
theta,
phi.
cos phi.
Phi.
Y is equal to
Uh,
sin phi.
R sin rho sin phi. Z equal to Z.
Yeah, and z is equal to z. So you will substitute this, and then you will put the limits, and then you can integrate. So now you are having
Okay.
idea. So just see the solution very quickly. You see, about the rho. So rho is lying between 0 to 2. So you see here, rho sin phi, rho cos phi, x, y, z is square. So z square is there. Okay. And 2 into 2 will
Okay.
become 4. So, okay. And as you said, rho d rho d phi dz. Okay.
Okay. Okay.
4 is already there. Sorry, not 2 to 4. 4 is already there. So 4 has been kept as it is. Now limit will be 0 to 2, 0 to pi by 2, and 0 to 3.
3.
Now you can integrate this rho d rho. It will be rho square by 2, and then you can put the limit. I think this integration you can do. Yes.
Yes, sir.
Okay. So finally you will get the answer as this one,
Okay.
72 coulomb.
Okay.
Like this, we are using the volume integral or this concept of the rho v. Like this, we are using. Okay.
Okay. Okay.
So this is one example. Just I wanted to illustrate so that you should get some idea that how it should be done. Right.
Yeah, okay, sir.
Okay. Then there can be the many one, but now I will come to this part. See, as yesterday also I said that rho L, this is the line charge density, which is nothing but, which means that the charge is uniformly distributed over a line. Means if I'm having a something a structure like this, so charge is uniformly distributed over this line, both sides like this. As you can see on this.
Okay.
So, so both sides, it is something like this. I hope you are able to understand. If any doubt, you may ask.
Yes. Okay.
Very good. So then, see, rho L is, that is the charge upon length. That is Q upon L. Right?
Yes, sir.
So, so we will see that what would be the expression of electric field for an infinite line charge. This actual expression you should know. Maybe derivation you may skip. So I will also not go in the derivation details. I will just explain the steps. But this result is useful while solving the numerical in the examination. Okay.
Okay. Okay.
So what expression we are going to derive is that the there is a C. You can see
Hello?
there is,
Yeah.
yes.
Yes, sir. Nothing.
Here you can see this is a see on the z axis there is a line whose length is minus infinity to infinity. Means this is an
Okay.
infinite line charge case. Okay.
Okay. Okay.
So, and here is a small element we have considered just to see the steps so that it will give you an idea that how the things are happening. So here we have taken a small infinitesimal element. So of course it is on the z axis. So its coordinate will be 0, 0, z dash. Right?
Okay. Yes, sir.
At this point P, I am interested to find the field due to this infinite line charge. Right?
Okay.
Now the one important concept we should understand here. Okay, the direction of the field will be like this. Of course, means it is away from, since it is a positively charged, so it will be away from the charge, so it will be away from this point. So direction of the electric field will be like this. Yes or no?
Yes, sir.
Yes. Now this is a vector. This will have the two components. One is this horizontal component and one is this vertical component.
Okay.
Now see, this wire has a symmetry. If I take this one as a origin, so above it is 0 to infinity, below it is 0 to minus infinity. Okay. Suppose at the same distance downward, try to understand this one. The same distance downward, if I take a infinitesimally small element, in this case, direction of the field would have been like this. Yes or no?
Yes, sir.
So again, if we will resolve this one, it will again have the two components. One will be the horizontal component, and another will be the vertically upward component. Yes or no?
Yes.
So if you see very carefully, due to symmetry, this is symmetry because just above z dash I have taken the below z dash. So due to symmetry, the vertical components they cancel out each other,
Hmm.
and we are left only with the horizontal component.
Components.
It will happen for every case. If suppose somebody is being a means interested that I want to take here, okay, you take here, it will be like this, angle will change. Again, similarly, somebody takes here, so again it will like this. So always this vertical component will cancel out each other due to symmetry.
Okay.
Am I clear?
Yes, sir.
Yeah. So now you see the this is what the concept is there. Then steps you can see. See, this DE, the first step, is of course, this one is the row axis. So DE row means row component, A row plus DEZ AZ. Of course, this D will have the two components. One will be along the row axis, another is along the Z axis. Of course,
Hmm.
yes or no?
Yes, sir.
Yes. Yeah. Then see, this is what it is saying. See, that this is what I said, that z component will go to 0, and this is what I have explained why it will go to 0. This will go to 0 due to symmetry. Yes or no?
Okay. Yes.
Yes. So once it will go to 0, so now we are finding the dE. So this is very simple. We are using the formula 1 upon 4 pi epsilon naught, that is k, dq r minus r dash. Yesterday I told you that this is the vector form of the Coulomb's law or the electric field. So r minus r dash means r dash, r is the final point, r dash is the initial point. So r minus r dash cube. Cube, yesterday you remember I said this, that
Yes, sir.
yes. So
Uh,
now we are just using the simple vector concept, and this will become rho square plus z dash square to the power 3 by 2. Why power 3 by 2, Betsy?
um, 3 by 2.
Yeah, why I'm writing this step here as 3 by 2? Why it is a power 3 by 2? From this step, how we are
Hmm.
getting to this step? I put 3 by 2.
Uh,
Hmm. See, it's very simple. Modulus of r minus r dash. So modulus means this, if you will take the magnitude of this will be rho square plus z dash square under root. And this to the power
uh,
3, this to the power cube. So if I can write this as the rho square plus z dash square to the power 3 by 2. This can be written, yes or no?
okay. Yes, sir.
Well, under root means this is power half.
Half.
Yes or no?
Oh,
Now I think this is clear. Yes or no?
yes, sir.
Yeah.
Yes, yes.
Now I will just integrate this one over the limit. So see, limit is of course minus infinity to infinity. So after integration, you will get a result. Actually, result is important here, and this result is very important. That E rho is rho L by 2 pi epsilon rho. Very important. And what will
Okay.
be the, and what will be the direction of this electric field, Bitsy? What will be the final direction of this electric field?
Along x-axis.
Not x-axis, along row axis, so along a row.
Row axis. Okay.
Okay, is this one. So it is not along the x,
Yeah.
it is a row. Okay. So this I'm already sending you the recordings, but still I
Okay.
ask you to note it down that electric
Uh,
field due to an infinitely linear charge conductor is given by rho L, where rho L is the linear charge density upon
Mm.
2 pi rho, 2 pi epsilon rho. So A rho, and direction is along the rho axis. It is A rho. Okay.
Yes, sir.
So one thing, one or two observation point here. See, this expression is independent of L. This expression is independent of length L. So
Oh,
length is not here in the picture. Means if you increase the length or you decrease the length, there will be no effect on this electric field expression. Are you getting my point?
yes, sir.
It is independent of length. So you should note down. Sometimes they conceptually they are asking something and we generally miss it out. But it is here. From here you can see this is dependent on rho L. This is inversely proportional to rho, but it is independent of length L. Am I clear?
But sir, royal is actually
Yeah. You see, rho L, rho subscript L is charge per unit length.
Q
This is a fixed quantity.
Q by L.
Yeah, but this is a fixed
Oh,
quantity. Rho for
okay.
for a particular wire is fixed.
Okay. Okay.
What I'm saying is that if you increase the L or you decrease the L, this expression is not going to change because this is a fixed quantity.
Okay. Okay.
Rho L upon 2 pi epsilon is not rho. And arrow is the
Okay.
direction of this field due to the
Mm.
line charge density. Okay?
Okay. Ah.
This you should take care of. Similarly, so this is what the final expression rho L upon 2 pi epsilon naught A rho. So this is what I have already said that the field falls off inversely with the distance to the charge line. So this is inversely proportional to the distance. Okay. But
Okay.
another important point to be noted here, in case of the point charge, yesterday we have seen this was kq upon r square. Yes or no?
Yes, sir.
Yes. There it was inversely proportional to a square of the distance. That is what is square of the distance. But here it is inversely proportional to only distance, and not the square of the distance.
Okay.
Remember, yesterday it was
Ah.
point charge. It was kq upon r square. So it was inversely proportional to a square of the distance. I asked you that if I half the length, then you said it will be
Ah.
4 times. If I double
Yes.
the length, then it will be 1 by fourth. So it was a square. It was inversely proportional to a square of the length. But here it is
Yes.
proportional the to the distance, not the square of the distance.
Okay.
Yes.
Oh, yes, sir.
So, so one example you can see here using the same formula. See, infinite uniform line charge of 5 nanocoulomb per meter is lying along the positive and negative x and y axis. This is lying on the positive negative. You can see here. This is the x, and here it is y.
Mm.
In the
Mm.
space,
Mm.
find the electric field at point 004 and at the point 0, comma 3, comma 4. Right.
Yes.
So see here I will use just a minute. Here I will use the result which we have derived because it is saying that infinite uniform line charge. So already we have
Okay.
derived that electric field intensity due to infinite line charge. So you see electric field at the point PA. So rho
Mm.
L x. Why I am writing rho L x? Because if you see according to the given figure, this direction it will have the two components. One will be along the, of course, this vector. One will be along the this axis, and one will be along this axis. Yes or
Mm.
no?
Yes.
Yes. So I will write the rho Lx. upon 2 pi rho 2 pi epsilon naught rho x a rho x means we are talking about the x component, and here it will be of course the y component. But this formula already we have derived, so we are using it directly. Okay.
Okay.
So now you see rho lx, the value I am writing it as a, now this value if you see 5 nanocoulomb per meter. So this is the value of rho L. Yes or no? This is not the charge. This is rho
Yes.
L because this is
L.
per meter per unit length.
Yes.
Thus I have substituted this value 2 epsilon naught 4. So why we are writing 4? Because here it is 0 at the point 004, only z component is there. So 4 we have substituted, the distance is 4, az because only z coordinate is there. So 2 pi epsilon 4 az. So now we will add this to very clearly, and then we can find. So it is very simple. So once we remember the formula, this is 44.939 AZ volt per meter. So electric field has been
Okay.
calculated at point A. Similarly, at point B, see what changes will be there. Again, it will have the two components. So now the change will be here is this one. The change you should know. Here the two coordinates are given.
Yes.
Here two coordinates are given. Okay, so two
Mm.
coordinates are given. So you see, rho x is okay. I'm putting it as 5, but why can you tell me how this has been written? 0.6 ay plus 0.8 az. Why we are writing this? Can you give me
Mm.
some clue?
Mm.
And why I am writing 5 here? Only this thing is important in this part. That's why the question here. This part is okay. This part, no.
Mm.
Tell me.
Oh.
See, it's very simple. You are not getting the point. It means, see, this vector I will write 3 ay plus 4az. Yes or no?
Yes. Yes.
I have to write, suppose this is my vector b. I have to write the
Uh.
unit vector. The unit vector will be 3ay
Mm.
plus 4az divided by
Mm.
magnitude of this vector. So what is the magnitude of this
Mm.
vector?
5.
5. So we will write 3 by 5. So what is the value of 3 by 5?
Okay. 0.6.
0.6 ay. What is the value of 4
Mm.
by 5?
0.8.
0.8 aj. And here, of course, we are
Okay.
writing the magnitude, that is the rho x, so that is the 5.
Okay.
So this part, actually this part, a rho x, this part is corresponding to this part. This rho x is 5.
Okay.
Are you getting the point?
Yes.
So this component, ay component is simple, there is no problem. So directly we can write that is the 2 pi epsilon naught 4, because ay this is only, it will be there. If you see the resolution there also you can find, because see the point is 0 comma 3 comma 4. So point is on the y and z. So y it is 3 and here it is 4. So this is my PV, that is 0 comma 3, sorry, 0 comma 3 comma 4. So it's but obvious if I take this vector here for the point B, it will again have the two components. One will be the downward direction and another will be in the this direction. So very easily it can be splitted into the two components. So one is along the AY component and one is along the AZ component. So AY and AZ. So now we have, sorry, AX and AY, the two components I can see here, AX and AY. And very easily it's the 5 into 10 to the power 9, that is a rho L by 2 pi epsilon naught rho times AZ. AZ is always the final direction. So now very easily I can put this value. So and then of course you can solve this. You can solve this and then you will get the value line. So this is how we are using the formula directly to the problems. A small problem it was. And so something like this can be asked. Sometimes it has been asked.
Okay. Yes, sir.
Did you understand this problem or any doubt
Y-
in any step?
no, sir. It's okay.
Okay.
It's fine. Yes.
Good. So, okay. Now we will go for the one more derivation and one more important result, that is the electric field due to infinite plane sheet of charge. This you have yesterday also I illustrated this result and I told that in your plus 2 level also you have studied this. So can you tell me what is the expression for electric field due to an infinite plane sheet of charge in terms of conductivity of the charge? What is the expression?
Mm.
Can you recall? Yesterday also I have illustrated it and you have studied it in plus 2. Of course, plus 2 it has been a long time since you passed plus 2, more than 7 8 years, but yeah, still. If you can recall, you have studied there at your plus 2 level sigma upon 2 epsilon naught.
Yes, sir.
Can you recall?
Yes, yes.
Yes. Yesterday also I told that here we are writing this as rho s upon 2 epsilon naught, same thing. And even I told you while teaching the flux that if you multiply that epsilon naught this side, so this is epsilon naught times
Uh,
E is called as D. So this and this term was called as flux density, and flux density for an infinite sheet of charge is given by rho s upon 2. Yesterday I said this, yes or no?
yes. Yes, yes.
So remember this, and this is derived here. Again, I will not go into much of the steps, but I will just let you know that how the derivation is being done. So again, we are taking a small a sheet which is placed in the yz plane, an infinite sheet in the yz plane, and again this is from minus z to z. So the thing is that here we are taking the this now again the components will cancel out each other due to the symmetry, of course, but this time it will be not the component, the it will not the z component, rather the horizontal component will cancel out each other. Why? Because we take the surface area normal component. If you can remember, if in my last week lecture I told that surface area is always taken normal to the. Okay?
Yes, sir. I remember.
You can remember. So this is what now only dEx is present, and this dEx is evaluated. I'm going a bit quickly because I'm interested in the result only. I don't want to give much of the time here. So this is what the my final result is of the importance. The derivations are in books also. You can go from there if any doubt you may ask.
Yes, sir.
So this is the rho s upon 2 epsilon naught. This is the another important expression. The previous was the rho L upon 2 pi epsilon rho, the last expression. It was something like that. And then we have seen the problems there. And here it is rho s upon 2 epsilon naught. Where epsilon naught is known, rho s is the same as sigma, that is the surface charge density. So rho s is nothing but the charge per unit surface area. Yes or no?
Yes, sir.
Yes. So this is what we are interested in this two, and very interestingly, we will derive this two expression very easily using the Gauss law in electrostats. Yesterday we have covered in a very hurry Gauss law. Today I will show you the application of Gauss law and how the same two expressions can be deduced using the Gauss law in electrostats. The thing is that whether it is from the Gauss law or the Coulomb's law, you should know and how to use this formula. That is the main part here.
Okay.
Right?
Yes, sir.
So this is another important part. There it was the arrow direction. Here it is always AN direction. AN. So meaning of the N direction is this is always normal to the seat. Here you see, this is
Mm.
important. sometimes regarding direction you may have a question, the conceptual question, that this is always normal to the seat and this is always directed away from it. So this, that is why
mm,
it is A. In the previous example, once again I'm writing here, it was 2 pi epsilon naught rho, A rho. So that was not
mm,
normal. It was in the on the axis. But here it is not on the on in that plane, rather it is normal to that plane. So this you should know.
mm.
Everything is are you able to understand the things or any doubt? Please keep on sharing in between. Otherwise, it will be. I will think that okay, everything is clear, and I will keep on proceeding. That may not be very helpful. So, so is it okay?
Yes, sir. It's okay.
Then this is what just shown here, positively charged and infinitely large non-conducting seat. So we will have the lines of force something like this, the positive for a positive test.
Mm.
So on that now comes the Gauss law and application. Gauss law already I have covered. So now I will
Yes.
give you the application using the same result. Flux, I have already told you that what is the meaning of the flux. Here, once again, you can recall integral form of the Gauss law. So yesterday
Mm.
already I have shown you the integral form. What is the integral form? Can you tell me? Already I have discussed this one yesterday. What is it?
Uh, uh, integral d dot ds equal to surface integral
Mhm.
d dot ds equal to
Yeah,
rho v dv volume integral.
yeah. And don't forget this side it is always the closed surface integral.
Close surface.
Here it is open surface integral. So rho v dv. Or here the same thing has been written. Only thing is here it is the E dot ds is written, but here if you see this epsilon naught has been divided here. It is the same thing. Either you multiply this
Okay.
epsilon naught this side, then you will write this as a d,
Then
or
d.
yeah, or you may write E dot ds. Then you will have to divide the epsilon naught this side. Means here you can, if you are writing E here, then it will be 1 by epsilon naught times rho v dv.
Absolutely. Yes.
It is the same thing, just a way of representation. Yes.
Mm. Yes, sir.
And what is the differential form of Gauss law?
Del dot d vector equal to rho v.
Yeah. So del dot D means you should also remember that the divergence of the flux density is equal to the volume charge density.
Density.
That means this is the divergence of the flux density is equal to volume charge density. Yes or no?
Yes, sir.
So this is what again, if in terms of E I am writing, then I will have to divide the epsilon naught here. You can see here, if I am writing E here, E as a R means E is of course always a function of R. So if I am writing del dot E, then I will have to divide the epsilon naught. If I multiply the epsilon naught here, then I will write this as a D, because D is epsilon
D.
naught times E.
E.
Yes or no?
Yes, sir.
Yes. Any doubt?
No, no.
Then, as I said, that application of the Gauss law. So, so we will derive the same that thing. The thing is that the for the application of the Gauss law here, you may see first thing is that you should remember that there is a limitation to the Gauss law. The Gauss law is applicable only to the surfaces which exhibit symmetry. Please remember this. For the Gauss law, you need always a Gaussian surface, and this Gaussian surface should always exhibit symmetry. Then and only then you can apply the Gauss law in vector styles.
Okay.
I will explain it a little bit more, but first you keep this in your mind that this Gauss law is having a restriction or
Okay.
limitation. What is that limitation? What is that?
It is applicable only to symmetric surfaces.
Yes, you always need a Gaussian surface. So that
Good.
Gaussian surface should be what type of nature it should have? Gaussian
Symmetric.
Yeah, it exhibits symmetry. One example we will take is that now again I want to derive the expression, or I am interested to find the electric field due to a infinitely plane sheet of charge. Though already we have derived, I know the answer, but now I want to derive the electric field due to an infinitely plane sheet of charge uh, using the Gauss law. So as I said, that infinitely plane sheet of charge is there. So to apply the Gauss law, I always need a Gaussian surface. So you see, here it is so as this is a sheet of charge, you may take a paper in your hand and you can just put it like you can just roll it. Just you can fold it like a rolling structure, and that you will find that a solid cylindrical surface will be there like this.
Ah.
Are you able to imagine it? Are you able to? Is it?
Yes, sir.
Yes. Is it convincing to you? Yes.
Yes.
So now you see, this is the positively. So electric field will be away from the seat. So the direction of the electric field will be like this. If I see this Gaussian surface, this you should understand very carefully. It is having the three surface. One is here, one, of
Mm.
course, middle one is here, and three is here, 1, 2, 3. And already
Mm.
we know that the electric field is always normal to the surface. Yes,
Yes.
normal
Yes,
to
sir.
the surface. Sorry, not yes. Electric field is normal to the surface. So see, if you take the area vector, that is the normal. So normal area vector to this one will be like this. This will be my area vector for this surface.
Mm.
Yes or no?
Mm. It will be.
Now I am asking that.
Mm.
Uh,
Mm.
or you tell me what will be the direction of the area vector for this surface?
Area vector.
Yes. What will be the direction of the area vector for this surface? Whether, okay, I'm giving you the hint also, whether this would be like this or whether this would be like this. Tell me. Yes, tell me.
Mm. Mm.
If this is your surface, this
Ah.
blue shaded portion, so what will be
Ah.
the, how will you represent the area vector? The concept of area vector is that it is always normal to the surface, outward normal to the surface. So what will be the direction? Whether this vertical side or this horizontal side? Which one will be the direction of the normal area vector?
Vertical one.
Yes. Not speaking. This will be vertical one. Then
Ah.
what is the angle, that is the theta, between the E and the normal vector? E is in this direction.
Ah.
What is the angle between these two?
0.
0. So, and again similarly here also it will be in the vertically downward. So, so angle will be again 0. Yes.
Yes. Yes.
You see very carefully about this portion. This portion, you see this unshaded portion. So what would be the, now the, if you take this surface, what would be the direction of the normal area vector? Would it be the same vertical or horizontal?
Horizontal.
Horizontal. Are you confident or you are just doing the guesswork?
No, no.
So it is this one. Now in this case, this is the direction of the electric field and this is the direction of the normal area vector. What is the angle between these two?
90.
90. Now you see, if you remember your Gauss law, the Gauss law was D dot ds. This was the my Gauss law. D dot ds is
Yes.
equal to Q enclosed. Yes?
Yes.
Yes. So D is nothing but E. So E dot ds. So now you see, for this case, means this is the E dot d dot ds for this surface plus d dot ds for this surface plus d dot ds of this surface. So d dot ds for this surface goes to 0 because dot means it is the cos theta, right? So
Yes, sir.
cos 90 is 0.
Yes.
So now I am left with here E dot ds. So E will come outside, and ds is integral of ds is a. So suppose area is a, then I will write E times a. See, very easy. E times a plus again E times a is equal to q in by epsilon naught. Yes or no?
Yes.
Because epsilon naught I have taken this side because there I'm interested. So this will become 2EA. Please understand this. If any doubt, please ask it. 2EA will be Q, and now Q in terms of rho s will be rho s times A. Yes or no?
Yes.
So I will write rho s times A by epsilon naught. So A gets
Yes.
cancelled, and what will be the expression of E? What will be the
Rho
expression
is
of E?
by 2 epsilon.
Yeah.
Rho is by 2 epsilon.
This we have already derived. Yes or no?
Yes. Yes, sir.
So, so this will be rho s by 2 epsilon naught.
Epsilon.
So here it is easily derived. No such means complicated integral, no such taking the infinitesimal, nothing limit. Very easily, just I defined my Gaussian surface symmetry. Just I was interested to know the angle between the E and area, and it was very easily derived. Yes or no?
Yes.
And similarly, we will see this is application. Similarly, I will see for this has been derived. This already I have discussed. So, and similarly, you can try for that infinite line. Just let me give you a hint. You can try for the infinite line. Here actually, just a minute. Here actually it's not there. So just or okay, one more presentation I'm having. There it is there. Right. This one, as already we have discussed this one. Screen is visible to you.
Yes, sir.
Yeah. So this one, the same. Again, see very clearly this PowerPoint or the PDF file is very clearly showing that this. You see, again, this is my line charge, the line charge conductor, and I am able to express and I am able to define a Gaussian surface, which is something like a hollow cylinder like this. Okay.
Oh.
And here we have already found that along this direction, along the R or the rho direction, the field is directed, right?
Oh.
Very
Yes.
quickly, I can ask you, that, see, this is my direction of electric field. So again, if I draw the normal on this, this will be of course vertically upward. So here, what will be the angle?
90.
90. So this will go to 0.
Yes.
Similarly, here also this will go to 0.
0. Yes.
And here it is E, and normal will be like this. So what will be the angle between these two?
0.
0.
0.
Now this will exist because cos 0 is 1. So now this will be left.
Yes.
Yes. So now I can easily find. So
Yes.
here. So this is what it has been found. See, E into ds. So what is the slant area or the surface area of a cylinder? 2 pi RL. Yes or no?
Required.
Yes.
Yes.
Here it is the charge will be lambda. Lambda here they are representing by lambda, but it is actually rho L. Same rho L or lambda. So rho L
Okay.
times L. Charge is rho L times
Oh.
L.
Yeah.
Charge upon epsilon naught. L gets cancelled. What is the expression of E?
Rho by R.
Tell me what is the expression of E?
Uh, 1 by 2 pi epsilon.
Hmm.
Uh, Rho.
Yeah. If I'm
Rho
writing
by R.
as rho as this R as rho,
Yes.
so, so same expression which we have seen.
Yes.
Yes. So this is what was the application of the Gauss law. We have seen that how the Gauss law can be used to find the thing. Uh,
Mm.
so Gauss law is over. Now I will go to the next topic. Better I would like to follow this one now. From here now, the another topic we will cover in the electrostars today is that about the electrostatic potential. Do you have any idea about
Okay.
electrostatic potential?
Uh, Potential means work done.
Yeah, work done. So work done here in electrostatic potential means work done of what sort of work done? What type of work done?
Uh, Work done by electric field.
Work done by electric field for what? Means work done for which purpose? What is the purpose of the work done? This is what I'm asking.
Okay.
So here you see this not having much of the idea, so it would be better. See, work done means if see there is a charge Q1 placed at some point, I'm interested to
Mm,
move this charge Q1 to this some distance. Okay,
mm, mm.
from A to B, or maybe anywhere. I may go from A to B here to here or here to here. So I'm interested to find the what amount of work done is required in moving the charge from one point to another point.
Another.
Okay? And
Mm.
from the simple mechanics, classical mechanics, you know that work done is force into displacement. Yes,
Yes.
the dot product
Yes, sir.
displacement. You see, work done will be force into displacement. And force yesterday I told you this is Q times E. Yes or no?
Mm. Yes.
Already we have discussed. DL is, we know that is a dot product, so I can write this as a DL cos theta, where theta is the angle between the field and displacement. Yes.
Uh, yes.
Now, one very important point in the concept point of view, why I am writing this negative sign here? Everything is okay. Why it has been substituted the negative sign here? See, why I am writing the negative sign? See, suppose, just try to understand this concept. I will give you a slight idea. There can be many more things, but the key point. See, if theta is lying between 0 to pi by 2, theta is lying between 0 to pi by 2, it means this term, if you means discard this negative, this term e dl cos theta means cos theta, this will be value of the cos theta will be positive. Yes or no?
Yes.
So means this entire term will remain negative. Now what is the meaning of this? If it is 0 to 90 means the electric field and displacement are in the same direction. Are you getting my point? What I'm saying is that if this means that electric field and displacement are in the same direction, means you are moving in the direction of electric field, not
Electric
against the
field.
electric field. This is what I'm trying to say.
Okay. Yes.
Is line between 0 to pi by 2, you can see here, this is the electric field, this is the dl, this is the theta. If theta is 0 to pi by 2, means you are moving in the direction of the electric field, not against the electric field.
Okay.
If you are moving in the direction of the electric field, then you need not to apply the external force. So who is doing the work? Work is done by the electric field.
Electric field.
If work is done on the system, work is done on the system, this is always negative. Okay?
Uh,
Now, case 2. Suppose theta is from pi by 2, it is greater than pi by 2. So suppose it is pi by 2 to pi. So if it is pi by 2
Mm.
to pi, then this value of cos theta will become negative.
Mm.
Yes or no?
Yes.
Means this entire quantity will become positive. Am I right?
Yeah. Yes.
Yes. Then if it is more than 90, means you are moving against the field. So means work is done
Mm.
by some external force. To overcome that force of the electric field, you are putting some external force which is overcoming this force of QE. So means this work is done by the external force.
External force. Oh.
So according to the classical mechanics, work done by external force is always positive.
Okay.
That is why this negative sign is there to count for this sign convention, that if work is done on the system, then it is negative. If work is done
Mm.
by the system, then it is positive. Or work done by the
Okay.
external force is always positive.
Positive. Mm.
See, this is an important concept. You may get the
I
conceptual
see.
problem. So, this is okay.
Mm. Yes, sir.
Now, I will very quickly we can come to the derivation. That is a very simple derivation that you see minus q e dl cos theta. So work done is equal to minus q1 by 4 pi epsilon naught 1 by r square dr. This is the nothing but the electric field, q1 by 4 pi epsilon naught r square. Dr is the
Mm.
displacement. So you are moving from r1 to r2. So this integration is a very simple one. So you get an expression that you see here, that work done, and this work done is electrostatic potential energy. So work done is minus q times E dot dl. E dot dl line
Hello.
integral. Yes, hello.
Hello. Nothing, sir.
Okay, some problem. Once again, I am repeating. Work
Mm.
done is, here I get an expression. This is minus q times a dot b integral E dot dl. So this is the line
Mm.
integral. See very
Integral.
carefully. Line
Mm.
integral over the path a to b. Line integral
Mm.
over the path a to b. And this
Mm.
W is called as electrostatic potential energy, and this is given as K Q Q1 Q2, if Q1 Q2 are the two separate charges, by R, not R square. If you write the R
Okay.
square, then it becomes the Coulomb's force. So see the very slight
Okay.
difference. It is K Q1 Q2 by R,
Okay.
inversely proportional to R, not a square of
Uh,
the distance. Please be careful.
um.
Okay. If,
Mm.
if by mistake if you put here R square, then this is force. This is not the electrostatic potential energy. This is force in that case.
Okay.
Is it clear?
Okay. Yes, sir.
So remember this expression. This W is electrostatic potential energy.
Mm.
And if you divide this Q here, if you divide this Q here, listen very carefully, then you will get the W by Q, means work done per unit charge. So this is minus of E dot dl, minus of E dot dl. And this
Mm.
quantity W by Q is called as, can you tell me? This W by Q is called as work done per unit positive test charge. This is called as,
Uh,
electrostatic potential
Potential.
energy. Electrostatic potential. So this is
Uh,
denoted by V. So V is
B.
given as W upon Q. So if you
Mm.
multiply with Q, then this becomes energy. Otherwise, it is
Mm.
electrostatic potential. VAB.
Uh,
Potential between the 2 points.
mm.
VAB is W upon Q, or you may write this as KQ by R. Another very important expression. This is KQ by R. And this is KQ by R square. This is the expression for which part? Yesterday we have discussed. KQ by R square is the expression of which quantity? Hello?
Hello.
I've asked a question that kq by r square is expression of which physical quantity? Tell me. Hello?
Hello. Yes, sir.
Yeah, tell me. This is the expression of, you have forgotten, this is the expression of electric field.
Please. Um,
See the difference, kq by r,
yes.
kq by r square. So
Got
this
it.
kq by r is, kq by r is what? kq by r is
Electric potential.
potential. kq by r square is
Electric field.
field. Then
Hmm.
kq square by r square. This is the expression of which quantity? If there are two
Electric
charges,
force.
force. And if I
Force.
write kq by k, if I write kq square by r, this is the which quantity? kq square by r. This is which quantity? This is electrostatic potential energy.
Energy.
Be careful. These four expressions
Yes.
are very, very confusing because somewhere it is q square by r square, somewhere it is q square by r, somewhere it is q by r, somewhere it is q by r square. So this four expression, please note down very clearly. Kq square by r square, that is force. Kq by r square, that is field. kq square by r, that is electrostatic potential energy, and
Hmm.
kq by r is electrostatic potential. And
Potential. Hmm.
this, and this you can remember by these two expressions. F is equal to q times E and W is equal to q times V. And W, that is the W, or some books are writing U also. U is equal to q times V. So this, is it clear till now or any doubt?
Yes. No, sir. It's okay.
Are you, so now there should not be any confusion between those four expressions, or still any doubt?
No, sir.
Now you see, the one important result you should remember, that work done by a static electric field over a closed path is always zero. Very, very important. The work done by a static electric field, remember static, not the time varying, because time varying it is not zero. I will cover in the upcoming lectures. By the static electric field is always zero over a closed path. Now you tell me, if this is written like this is a line integral, of course. If I use the Stokes theorem, in place of this, what can I write? Apply the Stokes theorem here. What can I write? E dot dl, instead of E dot dl over a closed path, apply the Stokes theorem. What I can write?
Del cross E.
Yes, very good.
Del cross E dV. Volume
Del cross E, then
dV.
dv. That is not correct.
Uh,
ds, you see here,
dS.
over the open surface is equal to 0, because 0 it is this side. So I can apply, see, very means practice Stokes theorem. Stokes theorem, see here I am applying the Stokes theorem. So del cross E dot ds is 0. Is it clear?
Yes, sir.
So from here I can write, because left right hand side it is 0. So can I write del cross E is 0? Tell me.
See.
And if the curl is 0, such field is known as
Okay. Conservative.
conservative field, or there is one more term,
Conservative.
conservative, or there is one more term.
Uh,
This field is known as
Irrotational.
irrotational
Conservative.
field or irrotational
Um,
vector. So this is very, very important. This is very, very important that this is irrotational vector. So remember that static electric field is irrotational in nature. Irrotational in nature, or it is also conservative in nature, means the work done does not depend upon the path taken. Please note this points. Okay, video lecture, this recordings I will share, but thing is that this should be noted in your mind, in your notes.
Mm,
Very important,
mm,
because questions are asked. I will show you the question. First, let me cover the
mm,
theory. And that's why,
uh,
without theory, question has got no meaning. If you don't know that that a static electric field is irrotational, and if it is something like that, true, false, or match the following, how will you? You cannot, because if
okay.
you don't know the fact, so anybody,
Mm,
if he or she does not know, how can you answer it? So once again I'm repeating, as I have proved also here, that curl of this static electric field is always zero, which means that this electric field is irrotational or static in nature. Sorry, or
mm,
conservative in nature.
mm.
Right, clear?
Yes, sir.
Yes. Be very very careful. Otherwise things will go wrong. So this is the few things. Yeah, and one last thing before I uh, end up the today's lecture. See, one thing is that V is equal to, remember this please, minus of E dot dl, minus of E dot dl. The electrostatic potential is expressed like this. Or in other
Mm,
terms, there is one more expression from here which is derived but very important. Electric field is equal to negative of potential gradient. Please remember this. If in your question potential is given and it is asked to find the electric field, you just take its gradient, put a negative sign, you will find the electric field.
okay.
Or vice versa, if potential is given, just see the path over which the field is to be evaluated, take its dot product with that, means in terms of the vector, and integrate it over the path C. You will
Mm,
find the potential. So these two relations are very, very important, because one is the scalar, potential is always a scalar, and one is vector, E
mm,
is always vector.
mm,
So this gives the
mm,
relation between the two, one scalar and one vector. If you take the gradient
mm,
of the V, put a negative sign, you will find the electric field. If you integrate the E with the path dl, taking the dot product over the path, then you will get the scalar term, that is potential. So this is very very useful relation, very very important relation. E is equal to minus of potential gradient and V is equal to minus of E dot dl.
mm.
Any doubt?
No, sir.
No. So today I will stop here. I will continue with the lecture on Wednesday. So Wednesday after 5 o'clock you are free.
Yes, sir.
So I will let you know the time, maybe on Wednesday or Thursday. After 5 o'clock,
Okay.
I will inform you. Then, uh, then perhaps in the
Okay.
next class I will go for some questions, because already theory
Yes.
almost we have covered the electrostats. So I will
Yes.
check it out that what sort of questions have been asked in the last 10 years or 15 years in the get from this
Okay.
topic. And I will
Yes.
discuss the few things and then very quickly I will move to the current part. Because
Okay.
okay. So till now it's fine. Are you solving the question by your own? Are you going through the things which are being taught to you?
Yes, sir.
Yes. So please be alert. Then only it will help you. Otherwise, your goal
Okay.
will be fulfilled. Otherwise, means
Okay.
unnecessarily you are giving the time and of course the later on the fee and the money. So means that should be utilized. Whatever you are paying,
Yes,
whatever
sir.
devoting the time and whatever you are paying, that should be worth. So this you should be able to
Yes.
solve the questions in the examination as much as possible from this topic, because you are
Yes, sir.
paying for it, you are giving the time for it, and I am also giving my efforts for it. So apart from fee, that is also the another satisfaction that yes, what I have taught, the my candidate is able to do that. So that has to be there. Okay.
Yes.
Yes. So, okay, thank you. Next class,
Thanks,
I
sir.
will let you know very soon, maybe on the
Yes, sir.
yeah, Thursday, and then we will proceed.
Okay.
Yeah, a little bit I will be, I'm going through the outlines, because as you have already given a deadline that by 10, 12th January you have to finish it.
Ah,
So a lot of things,
yes.
you have already passed out the BTech and you know that this subject needs time. So I'm trying my level
Yes, sir.
to give you the most important outlines so that you don't miss the questions. Otherwise, if I go on
Okay.
derivations each and every part, then it will go for the next 3 months. So that is of no use.
Yes.
At the time for the next 3 months. Okay.
Okay.
Trying my level best that I should cover those topics from where the questions are frequently asked, and you should understand
Yes.
that is how the question to be handled.
Yes.
Okay? Any doubt,
Yes, sir.
you please share it on the WhatsApp or